Last time we started section 4.4, and we encountered this thing called a second derivative, and we decided it's really not that much different than we've done before, right? We just have to do a derivative twice. And we did a couple of examples of those. This was one of them, and this was the other one. And we are on, I don't know if you will, it's basically example 3. Oops. Do I have a picture for it? Evidently not. Okay. I'll use this slide even though it's not the right one. All right, so the last example that I wanted to show you, the one that's on the blank spot at the bottom of your page, is I want to show you an example of what happens when you're looking at derivative and second derivative graphs. So you guys have done some examples of the original graph and the first derivative graph. In fact, the homework that you just turned in from the last section, 4.2, you did some of those, where you graphed the original graph and the derivative on the same set of axes, and you were trying to locate sort of the relationship between the maximum and the minimum and what's occurring on the derivative graph when that happens. So is everybody tracking with me? So you had a graph that looks something like this. So I'm going to draw the original graph, and based on the original graph, what we're going to do is we're going to draw estimates or sketches of what a derivative graph might look like, and then we're going to go on one step further and do what a second derivative graph might look like. So the graph that we're going to start with is going to look like this. And we're going to call this our function f of x. And what we know is that there is a special relationship between this graph and its derivative and certain locations on it. In fact, back in section 2.6, it was like one of your favorite sections, and you guys absolutely loved it on your test too. And I had you draw the derivative graph based on the other graph, right? You loved it. And one of the features that was very important when we were drawing those is to locate the places where the derivative here on this graph is 0. In particular, places where we change direction, right? Maxes and minimums or peaks and valleys, whatever language it is you like to use for that. And so on this graph, if you do that, you'll notice that that's right, whoops, here and right here, approximately, right? It's a peak in the valley. And what I would like to do on those places is I'd like for us to notice that if we come straight down to the x-axis, these are the locations where we're going to have x-intercepts. Let me use a different color, maybe green. Or we're going to have x-intercepts, it's not too bad, for the derivative graph. If we're moving from left to right, if we avoid sort of writing down detailed, itemized list of things, the first portion of this graph until I get to the first yellow dot, this graph is increasing, right? What does that tell us about the slope? It's a positive slope, which means the next graph that I'm going to draw is going to have a positive y value before my first green dot. So a positive y value would look something like that, right? Those values that I just drew in green are all above the x-axis, which means they're positive. Now between the two yellow dotted lines, the graph that I originally drew is decreasing. So what does that tell us about its slope? It's negative. So on the graph that I'm drawing right now, I want to draw a y value that's negative. It has to connect the green dots though, so it can't go too negative or I won't, get back to where I need to be. So I've got the bowl shape happening underneath. And then after the second dotted yellow line, the graph is actually increasing again, right? So what does it tell us about the slope? It's positive, which means the y value for the next one is going to be positive, and that means it's going to be where? Above. Good. So none of this is really brand new stuff, and a lot of the questions that you had on your, not a lot, but you had 2 or 3 of them on your last assignment, the one that you turned in on Tuesday, had you actually, like they gave you equations. They didn't even actually ask you to do this by hand, right? You just had to use your graph or your calculator to plug them in and to notice these relationships. So this part right here is review. What I want us to do is to go one step further. Let me label this first. This one would be f prime of x. What I want you to notice is that on this green graph, there is another location now that is another minimum, right? There's a minimum location on my new green graph. So the minimum location is right here. And I want you to draw a dotted line again from there back to the x-axis, okay? And I gotta have another color. How about, you wanna do purple? Okay. We'll try purple. Is this purple dark enough? That's too dark. Maybe let me do the lighter color one. That's not too bad. Is anybody in here colorblind? If you can't see a color on the screen, whether you're colorblind or not, though, let me know, because sometimes the colors don't come through on the screen the same way they look like on my iPad. So please let me know if you're like, yeah, that's not working for me, okay? All right, so we've got this line that I've tried to draw. It's not very big, but it's dotted back to the x-axis. And that location on the x-axis is going to be the location of a new x-intercept. So we're going to put it right here, that x-intercept, okay? Now, I want you to ignore the original white graph, and I want you to focus only on the green graph, okay? So before this location, where I drew my purple dotted line, the left-hand side of it on the green graph, what can you tell me about the graph? It's decreasing, which means its slope is negative. I've got a negative slope happening on the green graph before my dotted purple line. So negative means that it's actually going to have a y value that's going to be where? Below the x-axis. So I'm going to put a y value that is below the x-axis over here. Now, it may or may not be straight. It depends on the equations you're giving and so forth. But that's the most information we actually have. We're making this up as we go along to some degree anyway, because we don't have equations, okay? But it's at least below the x-axis. What happens on the second half of the green graph? The slope is positive, right? So if the slope is positive, then I'm about to draw a y value that's positive. And what does a positive y value look like? It's above the x-axis. So if you continue this yellow line on something like this, my yellow line is actually the second derivative. Now, yours may not cross the white graph or the green graph in the same location. That's not the point. The point is the relationship. And in fact, some of your questions you were asked say something like this: indicate the relationship between the derivative and the original graph. So something like that's the language they like to use. To indicate the relationship they're talking about is this dotted line business that I keep drawing. It's showing that the peaks and the x-intercepts for the derivative graph line up. Not only that, but there's something else that's really cool that happens. I'm going to go back to this purple line, and I want to extend my purple line to this location right here. And this is going to lead us into our next topic of conversation. So on the yellow graph, it was an x-intercept. On the green graph, it was a minimum. What do you suppose might be happening on the original white graph? Say it louder, Brooke. It is. It's an inflection point. It's the point on the original graph where the concavity changed. Can you see it? It's concave down before that location, and it's concave up afterwards. That's not a mistake or an accident. That happens every time. This is an inflection point. So let's talk about how we actually go about finding inflection points then. To find an inflection point, you will find where the second derivative equals 0. Now, just because the second derivative equals 0 doesn't mean it has to be an inflection point. It means it could be. It's kind of like when we found where the first derivative equals 0. It doesn't have to be a relative extrema, a max or a min, but it could be. It's the testing point. It's the location where it might occur. So we're going to find where the second derivative is equal 0. And that's going to determine for us if, in fact, we have a location where we might have an inflection point. And in the next graph, we actually have an equation to work with. Grab your calculator if you would. You've got an equation on this second sheet. What kind of an equation is this? It's logistic. Yeah, it's a logistic equation. Let's put this logistic equation into your calculator. You can put it into y1. So we have 45 divided by 1 plus 5.94 e to the negative 0.969t, or x. I've opened two parentheses, so I'll close two. And let's look at what the graph or what the question actually asks us. It says to graph P of t, P prime of t, and P double prime of t from t equals 0 to t equal 1. Indicate the points on P prime and P double prime that correspond to the inflection point of P. So this graph we know is going to be a logistic graph. And it told us it wants us to graph this between t equals 0 and t equal 1. So I can make my window go from 0 to 1. Now what's more is that from the original equation that you're given, you should know what the carrying capacity or the limiting value is. Now, I know it's been a while, but do you remember how to find that out from the equation? It's the top number, it's the 45. So the maximum value that I need over here in my window is 45. If you want to leave it at 50 or something like that, that's okay. But 45 is enough. Now I also remember from logistic graphs that they don't cross below the x-axis. So you could put that minimum on there as 0. Sometimes I kind of like to see the x-axis, so I'd like to actually have a little bit of a negative part on there. The other reason I like to see a little bit of that negative is because, remember, once we start like moving the values left and right, there's words that appear on the top and bottom of my screen, and it covers things up. So I don't really want to cover my graph up, so I kind of like to see a little bit more than is necessary. In fact, that might mean that we don't even want this to be 45, maybe we want it to be 60, just so we've got a little bit of buffer on the top and bottom so that things get covered up. They don't really cover up important stuff. So this is my original graph. Not very exciting. In fact, I get the feeling like this is not the window I should have had. Let me see here. I'm going to play with this for just a second. Let's make a change to our problem. Just change it to say from t equals 0 to t equals 10. I think that will make a better picture. It's probably a typo from some point in the past. So let's just make it t equal 1 to t equals 10. So go ahead and make your max 10. That's a better graph. Let's go with that. Can you see on here where the approximate point of inflection is? Like a guess anyway. You can kind of guess. Probably didn't need to go all the way out to 10 to see it, but you can kind of guess. It looks like it's somewhere around here, right? That little spot right in here. It looks like maybe somewhere around right here I've got an inflection point. So good, you guys? Okay, so in order to actually see this, we can do one of two things. The directions on the problem say that it wants us to graph P of t, P prime of t, and P double prime of t. Does it say it really wants us to find P of t or P double prime of t? P prime or P double prime? It doesn't. So could we find the actual equation? Look, could we actually find the derivative of this equation? Yes, the answer is yes, you could. But it didn't ask you or make a statement like it has to find that, right? So do you remember one of the things we did last time when we were in class is I showed you how to do the derivative without actually finding the equation? Yeah? Okay. We're going to do that back in this calculator at this point. So once you hit y equals, down here in y2, I want you to write down in deriv, so that's math 8. Our function is y1, comma x, comma x. Last time, if you had the calculator that looked like Hannah's, we talked that it pulls up this d, and you say dx, and you have, I think it makes you put in y1 here, and then x equals x. Yeah, thank you. Something like that if you have the other version of the calculator. So it's either this version or it's in deriv y1 xx. Do you have a question? Somebody said Dr. Hands. Yes. Math 8. So you get this component by hitting math 8, and you get y1 by hitting vars. Y bars function y1. Okay, has everybody got this part in y2? Okay, I'm just going to hit graph. I don't know if the window will still work for what I have, but we're going to give it a shot. And it isn't quite bad. That's not too bad, right? So one graph is logistic, the other one looks like it has a hill. And if you'll notice, this point that we thought was the inflection point is actually lining up right above the what? The maximum on the derivative. Okay. We didn't do the next part last time, but we're going to do it this time. Hit y equals. It says to graph the derivative and the second derivative. And this is actually the reason I didn't really want to find the derivative by hand, because if you find the derivative by hand, it was a logistic function to find the derivative. And you have had to do them before. That's okay. But when you find a logistic derivative, it becomes a product. So then not only do you have a product rule, but you have a really ugly, messy product rule, which means finding the derivative for the second derivative becomes more cumbersome as you go. So if I don't have to actually find the equation, I'm going to avoid it. There is one problem with doing that. The problem is that the calculator operates very, very slowly the more times you tell it to do this process again. So we're going to do math 8. But I don't want the derivative of y1. I want the derivative of y2, right? So I'm going to do vars y vars function, and it's number 2, y2, comma x, comma x. Or if you're doing it like this, you're changing where the y2 is in the y1 is in the parentheses to a y2. Again, I don't know if this picture is going to work within the same window, but we're going to give it a try. It's not so bad. So I want you to notice the original graph's inflection point became a maximum on the first derivative, and it became a what? A 0, or an x-intercept on the second derivative, right? This is the graph that we're going to sketch on our paper right now. Let me make one comment. I said it as I did it. I said, I don't know if this is going to work in the same window. You heard me say that, right? Let's say it didn't. It did not work in the same window. What would you do then? Well, you can turn y1 off, and you can graph y2. You can expand the window whatever you need so you can see what it's actually doing. You can manipulate. That's okay. When you're sketching these on the paper, it really is supposed to be a sketch. The point is not really what are the y values. The point is what's happening to this inflection point as it goes through the derivative graph and the second derivative graph. So if I'll grab my calculator, or not my calculator, but my iPad back up here, let me show you what happens when we're drawing this. So the original graph looked like this, roughly speaking, right? And we noticed that the inflection point was something like right there. And when I sketch the second graph, that is the derivative, I'm supposed to be making sure that the maximum happens there and then it dips back down. So this point's matching up, trying to match up anyway, to a maximum. And then when I'm catching up with these below, these should be dotted down here, I end up getting an x-intercept on the second derivative graph. It dips up, crosses, and then it comes back up like this. Drawn to scale? Absolutely not a chance. But the point is not the scale. The point is the dotted line. It's this right here. Actually, I'm going to circle it. That's the point. The point is the relationship that's happening between the three graphs at the inflection point location. You do need to label them. They actually aren't F, they're P's. I'll just change them. P of x, P prime of x, and P double prime of x. This indicate the points on P prime of t and P double prime of t corresponding to the inflection point of P of t. Mine are in purple, as long as you make a dot on them and you've got the dotted line connecting them, showing the relationship, that's what it's referring to. Good to go? Now, if you were back on your calculator, let me show you what this might actually end up looking like, because I know there's an example in either a homework or a group work problem where you're not going to be able to graph them all in the same graph. So let's say you were at the point where you were trying to graph the derivative, and it didn't work on the original graph. I've just turned this off by going on top of the equal sign and pressing enter. It turns the graph on and off. And then you can actually do zoom 0. Zoom 0 is an amazing feature. What it does is it changes the y max and y min to be a good graph for whatever you're trying to graph. So it manipulates it, and you can see that you end up with this graph. You can see the dotted line down here. Do you see it being barely dotted? It means the x-intercept is under, or the x-axis is under there. Close. It's not too far off, okay? But it's down there. And you've got the y-axis over here. You can see it dipping up. There's that maximum we're expecting, and then it's coming back down close to the x-axis. And you can do the same thing for the other graph. You can actually turn off y2, turn on y3, and hit zoom 0. And it will put it into a good viewing window in terms of the y's, ymin and ymax, on this. And you see how long it's taking it. See it scrolling over here? This is your calculator telling you, I'm thinking, I'm thinking, I'm thinking. If it starts scrolling really fast, it means you've paused it. And it's never going to do anything. Okay? There's the graph of the second derivative. And you can see that x-intercept that we were talking about right there. And you can see very clearly it does, in fact, have a peak in the valley and come back near to the x-axis. So you can manipulate the y-axis to do that. On this graph, this is kind of cool. If you've got this graph graphed right now, it's easy enough to find that x-intercept location. We've done that before. And part B on this problem says to find the inflection point. Agreed? Okay, so we need to find the inflection point. And this location right here is the x value of the inflection point. But I'm going to go back into y equals and turn on y1. I'm not going to regraph it so that I care about seeing it. I'm just going to turn it on. Okay, I'm going to hit graph. It doesn't need to be on for what we're about to do. Yeah, I mean, it could be on. It wouldn't hurt anything, but it's not necessary. Okay, so this is graphing again. All I'm seeing is my second derivative graph because this particular window is not a good one for y and y double prime. Okay, so we're going to find the x-intercept. So we're going to do second calc. Right now it says y1 up here. If you've got y2 on as well, that would be a problem. You need to make sure you're on y3 because y3 is the graph I'm seeing in my window right here. I'm going to arrow over here. Actually, I'm going to hit second calc 0. I want to find the 0. And I'm going to arrow over on the y3 graph until I am on the left-hand side of the x-intercept. And I'm going to hit enter. And it says right bound. I need to be on the right-hand side of the x-intercept and hit enter. And then guess means sort of close to the point. And this is the x value of the inflection point, 1.839. Okay? But I did this last time. How can I find the y value of the inflection point? You can arrow up. Good job. Well, good job remembering. Okay, so if you arrow up, it puts you back on the y1 graph. There's that 1.838 or 839, and it tells you your y values inflection point for the original graph at 22.5.
What?
What? It should. Maybe you're on y2. Double check. Okay. And make sure you're on y1. Now I want to show you something kind of cool. Hang on. Come on now. There we go. So your inflection point on this graph is 1.839, comma, 22.5, right? We haven't answered the second question, but I want you to compare this y value to the original function and see if you can find a relationship between that 22.5 and the original equation. Say it loud, Brooke, you got it.
It's half of the limiting thingy.
It's half of the carrying capacity or the limiting value on top. The limiting value on top is what? 45. And the inflection point always happens at half of the limiting value. So that's a good rule of thumb. If we had not gotten a 22.5 here, we should have been concerned. We made a mistake somewhere. So 22.5 makes sense. Now thinking about the original graph here, this location right here, that's my inflection point. We're going to answer the second part of this question. It says, is it a point of most rapid or least rapid increase? This location, it's increasing. Agreed? Yeah, it's increasing. Is it increasing the most rapidly in the nearby area or the least rapidly? It's most. It's the steepest part of the curve right there. And that's what an inflection point is. It is a steepest part in a nearby area anyway, or it is the flattest part, depending on what the graph is doing. So this is a most rapid increase of the nearby locations. All right. The next equation, or the next problem, actually gives us another equation, but it asks us something different than the last one. Here's the median size. Median is an average size of a new single-family home built in the U.S. between 1987 and 2001, modeled by this equation, X years after 1990. And part A says that we're going to actually find what? Yeah, we're not going to just use the calculator to graph things like we did in the last one. We're actually going to find them. So we're going to find the derivative and the second derivative. So h prime of x. What is the derivative of 0.359 x cubed?
1.075 x.
Good. Now we need the derivative of 15.198 x squared.
30.396.
And then x, right, Lainey? Yep. And then the derivative of 221.738x.
Just 221.7.
Okay, and then what's the derivative of the 826.514? 0. Good. All right, now, this uses the word models. A model has 4 parts, right? 4 parts. Caleb might be dying. Not sure.
How about I say equations?
4 parts.
Equations is my favorite.
Step 1 is a name. Does this equation right now have a name?
Yes.
Yes, so we're done with step 1. Step 2 is an equation. Does what I have written down, is it an equation?
Yes.
Yes. What's step 3?
The units.
The units of the output. Okay, so what are the output? The output of our original function here is square feet. So what are the output units for the derivative? Square feet per year. It's always output per input. So what I want to write down now is I want to write down square feet per year. So I'm going to make mine a little bit smaller so I have more space. All right, so my units are square feet per year. Okay? Name, equation, output units, and then I need to write down the input units. What are the input units for my new equation? Yeah, they're exactly what they were before. So there's no, well, I mean, there's some thinking, but there's very little thinking on that part. It's just a copying part, right? So X years after 1980. That's my derivative. Now I need a second derivative. So what is the derivative of 1.077x squared?
2.154x.
Okay, and the derivative of 30.396x. 30.396. And then the derivative of 221.738. 0. Cool. And I've got the first 2 parts done, the name and the equation. Third part, output units. What will the output units be for the second derivative?
Square feet per year.
Yeah, square feet per year. And I know that sounds funny. Just write it down. You will also write.
Per year squared.
You could say per year squared. That would be fine. So we're going to write down one of those 2 versions, square feet per year per year. And then what?
X years after 19.
Yes, X years after 1980. Okay, ready for part B? Yeah? Okay, part B says, determine the time between 1987 and 2001 when the house size was increasing least rapidly. This phrase, whoops, is one of those keyword things. Okay, so we've had some keywords along the way throughout the semester. One of the keywords was model, and model means it has 4 parts, okay? That was a keyword. We had a keyword that's a key phrase that says rate of change. Rate of change means slope or derivative, yeah, depending on the context that it's used in. And so this one is one of those keyword phrases. This keyword phrase where it says increasing least rapidly, increasing most rapidly, decreasing least rapidly, and decreasing most rapidly. Those 4 phrases all mean inflection point. So anytime you see this phrase, it's asking you to find an inflection point. So jot that down in your notes somewhere. It's an important phrase. This tells you find an inflection point. So it wants to know between 1987 and 2001, what value, what x value, what year, if you will, has the, or is the inflection point occurring in. And then it wants you to find the corresponding house size and rate of change in the house size at that time. This is just a hangover from the last screen. That's what happens when you copy paste so much. Okay, mark that out. Okay, so take your calculator, and I want you to put in the equations you just found. And I know you're probably going to be a little bit tempted to use inderiv, aren't you? And you can if you'd like. It's not going to hurt anything. There is a downfall to inderiv on your calculator. The downfall is that it takes it longer. And in some cases, that can be really annoying because it creeps along. So I'm going to enter my equations because we already found them as I found them. If you want to use inderiv, it's not going to hurt anything. But just be aware that it will make it slower. So 0.3959x cubed minus 15.198x squared plus 221.738x plus 826.514. And then I'm going to use the derivatives that we had found before. I need to pick a window. Now, how is my equation being measured in this problem? How is the input being measured? Let me say that. Years since 1980. Okay, it's being measured in years since 1980. And they tell us they want us to find the inflection point between 1987 and 2001. So what x values is it giving us as the endpoints to look between? 7, that's my minimum. And the maximum? 21. 2001 is 21 years after 1980. Now, I don't know what my y-min and my y-max should be. I have absolutely no idea. So I'm just going to put those at, I'm not even going to put them at anything. I'm going to try zoom fit and see if it'll zoom fit all my screens. I don't know if it'll work. We'll see. Ooh, look how awful that is. Royally terrible, right? I told you on the last problem that it doesn't work to always do in the same screen. If you put minimum 7, maximum 21, and tell it to zoom fit with all 3 of your graphs showing, it's going to look something like this. Does everybody's screen look something like that? Yeah? So let's go back and let's make a change. Let's only graph y1. And I'm going to hit zoom fit. That's much more pleasant. Yes? Looks like a cubic graph, which makes sense because it's supposed to be cubic. You knew from the original equation, though, it's sort of residing up here and, it's high from the way it was drawn before. So as we're drawing this graph over here on your paper, we're going to draw a cubic equation that's really high up. Something like that. It's a little bit more flat than I meant to do it in the middle. So this is H, right? And we know there's an inflection point here. You either see it or you remember that the notation, right, what we sort of circled above or boxed in above, talked about inflection point. So it might be wise, and I think it's helpful, if you go ahead and mark approximately where that inflection point is and mark it down to the x-axis because that's going to have important significance later. Now back on your calculator, Let's turn off y1 and let's graph y2. Zoom fit, zoom 0, remember. And it's a parabola. Should be no surprise. You knew it was a parabola. Your equation said so, right? It's going to be a parabola. Where is this minimum occurring? I don't mean a specific value, but, huh?
On the x-axis.
It's almost, right? It's dotted line. It's not actually on the x-axis, something else. At the inflection point. That minimum is occurring at the inflection point. So back on your calculator, or on your paper that you're drawing, and on my iPad that I'm on, we're going to sketch a parabola graph. Again, the scale is not important. I don't care that my scale is right, like not one bit kind of care. But I do care that when I draw this graph, that I'm hitting the minimum right here. At least I'm trying to draw it in such a way that I am. And it's occurring still above, it might be closer to it than I've drawn it, but above the x-axis, because I didn't see the x-axis actually show up solid on my screen. Okay, so that's h prime. And let's turn y2 off now and turn y3 on. And we're going to hit zoom fit. That's zoom 0. And what do we see this time? Straight line, right? It's a line, which again shouldn't surprise us. We had a straight line written down as the equation. Of course it's a line. And it's a line where it crosses the x-axis. And where is it crossing the x-axis? At the inflection point from the original graph. So again, back on our paper, when we're drawing this, we're going to draw it to represent that fact. Something like that. And that's h double prime, second derivative. Says graph the 3, indicate the relationship between the inflection point and the corresponding values. That's what we did on C. I guess I just did C, didn't I? But that's okay. We needed C and B to be done together anyway. So this is C, my bad. But B asked us to find the point of least rapid increase, and we need our graph to do that, so that was all right. Go ahead and hit y equals. Turn on y1. You can turn y2 on if you want to, but you don't need to. So we need y1 turned on and y3 turned on. And if you've still got it in the window from earlier, it should still look like the line graph. Okay? So we're going to hit second calc. We're looking for that intercept location, that x value. That's a 0. Make sure you're on y3. Right now I'm on y1. So I'm going to arrow down until I get to y3. It says left bound. So this is the left-hand side. It says right bound. Now I'm on the right-hand side, and I'm going to guess somewhere roughly in between. It says that it's the x value of 14.111. That's the x value. That's not the inflection point, right? But that's the x value. How can I find the other pieces of information? Because it said, determine the time when it was increasing most and least rapidly. Well, this is the time. The answer to that question is 14.111 years after 1980. Okay, I mean, that's the answer to that question. But it also says find the corresponding house size and rate of change in the house size at that time. How am I going to find those? What do you have, Kendra? Arrow up. What will that find? Right now, my screen's only got y1 and y3 on it because I didn't turn y2 on. Maybe I should do that first. Let me turn y2 on. Let me start again. Let's turn on y1, y2, y3 because we're going to need all of them actually on eventually anyway. So graph, there's still my graph. Oh, look, there's that parabola graph up there hanging out in the middle of nowhere. Okay, I'm going to try my 0 again on my y3 graph. Left bound, right bound, guess. There's the 14.111 again. Okay, so over here on your paper, the when is 14.111 years after 1980. If I arrow up or arrow down to get to y1, what was the equation of y1 talking about? What did it tell me? Like, look back at the context of this particular problem. What is h? What was it, Brooke? Square feet of a house. It's the size of a house, right? So if I arrow up and you see this number down here, this is 1937.941. It's 1937 and some change, almost 1938 square feet. That's what y1 tells me. It's the original graph. It's the house size. If I arrow down again to get to y2, see I'm on y2 now? This one actually tells me how quickly it's changing. What's it say? 7.273. What? What are the units on y2? On h prime? We wrote them down.
The square feet per unit.
Square feet per year. Okay, so let's do this all together. We'll write it all down now because we found the numbers. Okay, so this is actually here. Put them on the right slide. That's the slide there. This location that I'm finding, I just found out a minute ago that this x value is 14.111. That the y value here, obviously it's 14.111 for x. The y value from here was 1937 point, what was it, 941. And at this location it was 14.111. And it was 7.273. That's the numbers I found. But whenever it talks about the problem, we're supposed to be interpreting, giving an answer into something that makes sense. Because it says that we're supposed to be finding over here the time, that's 14.111, years after 1980. That's the easiest way to write it. If you wanted to talk to me about this and say that it was in 94, or even 1995, depending on how you're rounding things, it would be okay. But it's 14.11 years after 1980. The house size, what was the house size at that time? We did it over here. What's the house size?
1937.
Right, the 1937.941. And what are the units on house size here? Square feet. You can either write the feet with the little square next to it, or you could write out square feet in words. That's fine too. And how is it, what did it say? Changing. What's the rate of change? What was the rate of change?
7.273.
Yes, 7.273. Square feet per year, feet squared divided by years. Some version of those notations will work just fine. Square feet per year. All right. Let's do one where we've actually got to create a model now. Y'all ready? Grab your calculator. It says this table gives total emissions in millions of metric tons of nitrogen dioxide in the U.S. from 1940 to 1990. Part A says to find a model for the data. So go ahead and clear out Y1, Y2, Y3. In your stat menu, stat is where we plug in data. So you hit stat, edit. If you have everything in there already, you can clear on top of L1, clear on top of L2. Sometimes it's possible to actually enter the data exactly like it's given for years, but usually that's not the cleanest way to do it. So this says 1940, 1950, 1960, and so forth. And I'm inclined to make 1940 year 0 and go up by 10s from there. So I've got 0 to 50 for my years. The output values, we never enter into, we always enter them exactly like they appear. 6.9, 9.4, 13, 18.5, 20.9, and 19.6. And this happened on your homework last night too, just like it's stated in here right now. It just says find a model. It doesn't always tell you if you have to find a specific type of model. And when it doesn't tell you that, it means you've got to make the decision for yourself. So if you hit y equals, you can go up to plot 1 and turn it on by just hitting enter on top of it. Zoom 9 is your stat window. And it looks something like this. And you have to decide what is appropriate to try for this particular model. And if you'll remember, the first question when you're trying to decide upon a model is to ask yourself, does it change concavity? That's the first step. And does these dots seem to change concavity? They look like they do. Over here it looks like there's some concave up stuff going on, and definitely you see the concave down over here. Okay, so concavity looks like it changes. So if you change concavity, what are the choices for what might work? Cubic and logistic. Very good. So those are our only two choices. Now, is logistic going to work on this? What's wrong with logistic for this one? Yeah, this is definitely dipping back down over here, and logistic doesn't do that. It levels off. So cubic is really our best bet to try on this. So that's what we're going to try. So back in your regular screen, you're going to do stat calc and look for cubic regression. Depending on what yours does next. Mine tells me to put in y1 right here. I know some of you have to arrow down until you get to y1 in your calculator. This is my equation. Now there's something happening in this equation that I want you to be aware of. It happened on your first test. I didn't take off for it in case you didn't see it. But you do need to know that it matters. Do you see the capital E right here? Yeah? Do you see that on your screens as well? Do you know when that shows up, what it means?
Scientific notation.
Good. It's scientific notation. It's your calculator's way of telling you that means that it's times 10 to that exponent, to the negative fourth. So as we're writing that down, we need to be aware of that so that we can include that appropriately. So we're going to write down this equation. So our cubic equation, oh, we need a name for it. What do you want to name it?
L of X.
L of X for Laney, right?
Yeah.
I've had people do that consistently, actually. All right, L of X equals negative 3.611. And then we need the times 10 to the negative fourth. I would encourage you not to use the X for times because there's an X in your problem for the variable. Either use a dot for times or some parentheses that indicate multiplication. Don't use an X. So times 10 to the negative fourth, X cubed plus 0.023 x squared plus 0.013 x plus 6.990. That's our equation. Oh, we didn't hit graph. Maybe we should have graphed this just to see that it works. I'll show you that it does. It's a good idea to graph things and make sure that our guess as to what we thought it was going to look like really worked. It's nice, right? It's a very nice fitting equation. Okay. All right, are we done with this model? No, what's missing? All sorts of units. We've got a name, L of X. We've got an equation. What's next? Output units. What are the output units on this problem? Yes, it's actually the millions of metric tons, and you can say of nitrogen dioxide. You can write it if you really like, just like they've written it here. That's fine. It's not going to hurt anything. It's the units that say the million metric tons that are the most important part of that. Million metric tons of nitrogen dioxide. That's my output units. What are my input units? Good. So if you entered 1940 as year 0, you have to write down that this is X years since or after, depending on how you like to write that, 1940. Because you put 1940, I anyways did, put 1940 as year 0. That's my model for this data. What does part B say I'm supposed to do? The slope, which means what, Luke? What am I finding if it's asking me for a slope formula? You get the derivative, right. That phrase slope means derivative. All right, good. So we're going to find the derivative, which will be called L prime of x. And in our problem, we had 3.61 at the beginning, and we have an exponent on x of 3. So if I multiply the 3.61 times 3, or 611, I get 10 point what? Is it 833? I still have the 10 to the negative fourth, okay? But now it's x to what power? It was x cubed, now it's x squared. And then I need the derivative of, what do I have next? 0.023 x squared. So what do I get for the derivative of 0.023 x squared? Going once, going twice. 0.046, right? X. And then I need the derivative of 0.013x. Yep, just that number by itself, 0.013. And the other part was constant, right? The 6.99 constant, so I don't need it. Units. What are the units for the output on this particular problem?
Million metric tons per year.
Good. Million metric tons. If you want to say of NO2, you can. And it is per year. What's missing now? The input, yeah. Which should match exactly what we had before, right? X years since 1940, 1940. Oh, we left the interval off. Yes, I'm sorry. You're right. So this one would be 0 less than or equal to x less than or equal to 50. Good catch. All right, there's one last problem in this section, and it says, determine when the emissions were increasing most rapidly between 1940 and 1990. Give the year, the emissions, and how rapidly they were increasing. Okay? So what's it asking me for? The inflection point. Increasing most rapidly is key phrase for inflection point. So let's let our calculator do all that. Now on this one, I'm going to go ahead and use nderiv. Just because I don't want to enter all the times 10 to whatevers. I already have the original equation in y1. I don't need to type it in. It's there already. So I'm going to turn off the plot. I don't need it on. I'm going to do math 8, y1, comma, x, and then in y3 I'm going to do math 8, y2, comma, x. And what I want is the graph of y2 turned on, y3, turned on, and the other two turned off. My window has already got the right parameters on the starting and the ending point because it already did the dot plot to start with, so I don't have to manipulate that. I can just do zoom fit, which is zoom 0, and it will look for a good window for y3, which we expect to be a line, right? Because it was cubic, and then quadratic, and then it'll be linear. Graphs a little slowly. It's really a lot slower if you try to do it with a logistic, but not as bad if you do it with a quadratic. And it's that intersection with the x-axis, or that x-intercept that I'm interested in. But I'm going to need y1 and y2 turned on in a minute, so now I'm going to turn them on and just regraph. Not restructure the zooming, just hit graph again. Now I've got part of this weird graph showing up over here on the left, and there it is on the right. don't care. I don't care about any of that. I care about the intersection of the last graph I just saw. So I'm just going to wait till it shows up again, and it's right there. So I'm going to hit second calc, 0. Make sure that I'm on Y3, because I've got lots of graphs going on there. There's my dot, and it says Y3 up there. I need to be on the left-hand side, and then I need to be on the right-hand side, and then I need to be close to the value, guessing in between. And it's thinking, and it's thinking, and it's thinking, because it's going through the indirective command to do it. And there's my x-intercept, x value, 21.077. That's a number of years. Tell me, is years what? Yeah, it's years since 1940. It wants to know the amount of emissions in that year. Which equation will give me the amount of emissions? There are 3 equations on my calculator right now. There's the original, the derivative, and the second derivative. Which one gives me the amount of emissions? The original. So if I go up to y1 and I look at the y value, it's 14.037. So the emissions is 14.037 what? Metric tons of nitrogen dioxide. And then the other question it says how rapidly they were increasing. Which equation answers that question? Y2, the derivative equation. So if I arrow down to Y2 here, I have the answer down there is 0.495. .495 what? Metric, that's okay, metric tons what?
Oh, per year.
Yeah, metric tons per year. Okay, any questions on that?